So here's Ben Sherman. Take it away.
Okay. Hey guys, so I'm a grad student over in CSAIL, so I study programming languages. And so this talk's basically going to be about a way of computing with continuous values. So think like the real numbers or other continuous things that are like the real numbers. And so basically, you know, what's normally done, right, is we... Oh, so by the way, we just published a paper on things related to this, so if you're interested in some more information on it, feel free to see the paper. I can send you the title or something if you're interested. But so the basic idea, right, is that when people implement algorithms that have to do with continuous values, for instance, geometric computation, as I'm showing here, they think about it as real numbers, but then they implement it with floating point. And most of the times we don't think too much about that, but that's a little bit scary. And so here's a little bit, one example how, you know, amidst many. So in geometric computation, here's a very simple primitive that's often used. So you have 3 points in a plane, A, B, and C. And you want to know, do they form a left turn? Do they form a right turn? Or are they collinear? And so you can specify this as a real number algorithm, but the thing is, if you get something that's like really close to collinear here, you can imagine that just because of floating point error, and you do see this, if they're pretty close, you can end up making the wrong answer. So this is actually a left turn, but it might decide, nope, I think it's a right turn because of the floating point error. And it doesn't seem too bad because it's only like if you make a small mistake there that you'll get the wrong answer. But what happens is then, you know, someone comes along and says, I'm going to use this primitive in a larger operation. So here we're seeing a computation for computing the convex hull of a set of points in the plane. And so if you're not familiar with the notion of convex hull, basically imagine an elastic band going around all the points, and the convex hull is the ones that will be hit as you let it contract. So here's a set of points. It includes this point x here, which is supposed to be in the convex hull, but the thing that the algorithm computed is the green. So the reason it missed the x is because it's using this left-right turn primitive inside the algorithm. And so what happened is at first it started out making a convex hull with A, B, and C, and then it said, okay, is x inside the convex hull of A, B, and C? And so B and C are both really close together over there. And it said, I'm actually inside A, B, and C. Because it screwed up on the left-right turn for one of those edges. And so you end up getting an error. So this is kind of what happens if you think about your programs as real numbers and you design algorithms thinking of them as real numbers, but then implement them with floating point. You get what I would call here unsoundness, right? This is, and here it's not even close, right, to the real answer. Unlike the previous slide, this is not even close. So this talk is about a sound way of computing with continuous values. It's not particularly efficient necessarily, but we're exploring how you can do things soundly at all. And it turns out that some things become very difficult to even compute at all when you compute soundly. So now I want to show a little bit of a demo for the language that we have for computing soundly. So the sort of plan for this talk is 2 pieces. First, I'll show a little demo, and we'll look at how to program, and we'll sort of see what the language is like. And then the second part is more exploring the semantics, particularly the higher order functions. And so in there, we'll also kind of go through, well, okay, how do we take the syntax and how do we interpret it into categories? And so basically, we'll look at the meaning, particularly of all the higher order functions that we'll see in the language. So if you guys want to focus on like more one aspect or another, just feel free to like let me know, or something like that. Okay, so let's start with the demo. First of all, what do I mean by computing soundly? All right, so on the bottom here we have Python. Let me know if you want me to make any of these things bigger. So here's a really simple computation in Python. So we take 1 we add a giant number and then we subtract it again, and we know using real number reasoning, right, this is 1. But we get 0, right? And this is, if you're familiar with floating point, this is an obvious error that we get because, this is what they call a catastrophic cancellation. But on the top here, we'll use Marshall, and so we'll give the same expression, and we get something different. It's a little bit crazy. Let me just do it again. So the interface is a stream of approximations to the number, and in this case, it ended up actually getting to an approximation that was perfect with no error. But you get a stream of approximations, all of which are true about the number, right? So it's definitely between -2 to the 90 and 1 to the 90, and we progressively get better and better and better until we get the actual answer. So this is what it means to be sound. As you can see, it was a lot more work, but it did produce a right answer. And so all the mathematical laws, so for instance, we just saw a violation of a mathematical law that we saw for floating point, for instance, here in Python. And so, we all know that if you take the square root of 2 and you square it, you get 2 back. Close, 2.004. So let's see what happens when we do the square root of 2 in Marshall. Okay, so again, we're getting a stream of approximations. It's definitely within 0 to infinity, right? It's definitely in here. And we see all of these contain 2. And I've just set an arbitrary cutoff for it to not produce like really, really long streams of decimals. But you can see here that we are getting intervals that will always be containing 2. And so that's what soundness means here, right? Because the true answer is 2, we'll always get intervals that always contain 2. And there's also a notion of adequacy that for these answers that if you wait long enough and you have some tolerance that you want to know the answer up to a given tolerance, eventually you'll get an answer within that tolerance. Right, so we can do, play more of these games, right? If you weren't worried about that 2.004 being so far from 2, well, now we, just violate more mathematical laws, right? Just, sort of, once we have a small error, we can turn it into a large error. And that's what happens with the left-right turn primitive, right? A small error becomes a large error. Whereas here, you might not say here that the answer in Marshall is much better for this. So we get non-termination, we get a stream of question marks. And so the return type of this expression here is in this sigma. So this is called the Sierpinski space. So it corresponds to the Sierpinski space of topology. And basically you can think of it as semi-decidable propositions. So if I do something that's false like this, I get non-termination. But if I do something that's true, 0 less than 1, that's easy. It says, yeah, true. Okay, so just one last example. We all know that the sign of pi is 0. Oops, don't need that there. But it says not 0 here. Whereas if we do sign of pi in Marshall, we will get a stream of intervals that all include 0, right? Because 0 is the right answer. Okay, so let's look a little bit at some more complicated things for programming. So the main first thing that I want to look at are, basically, I'm going to look at 2 different examples that are going to be very related to each other. So the first is about solid modeling. How can we do computable solid modeling in this manner? And so we'll end up defining a type of K-shapes here. And I'll explain this later, we'll get into it, but so if you guys, I don't know how familiar people are here with functional programming notation, particularly in terms of the types. The main thing just to keep in mind is if you see a bunch of arrows, like this, it's associated this way. And so the key thing is if I have something like this, this is really equivalent to if you give me an A and a B and a C, I'll give you a D. So Over here, though, what we see is what we call like a second order function. So this is a higher order function because it takes a function as an argument. And so we're going to use these to represent shapes. So think of it like, really it's a space of compact subsets of a given space. And then we'll go to measures, which are very similar. So this has the same exact form, except instead of going to that B, it goes to an R. Okay, so let's start out by basically seeing what these shapes are. So the idea here is B is a space of logical values, but it's not the Sierpinski space, it's actually pairs of Sierpinski space values. So just before we get into the definition of K-shapes here, I'll get into the definition of this B, which we call the Belknap quasi-Booleans. And so the thing is, right, if we have this semi-decidable values, any questions here?
What's a Serpensky space?
What is the Sierpinski space? So I wasn't planning to get much into topology, but I'm happy to do it. So Sierpinski space is a space with 2 points, true and false. And it essentially has one non-trivial open set, which is around the true. So I can observe if I'm true, but I can't observe if I'm false. I think that's all I have to say about it.
So when you said that 2 smaller than square root of 2 squared
Yes.
is undecidable, you meant it in this case. But like we know that like 2 equals square root of 2 squared.
We know it. So
why?
the general problem that you phrase in terms of comparing two real numbers. So you could ask about, if I have two real numbers, can I have a continuous map into the Booleans? And this is the fact, right, the plane is connected, so there's no continuous map into the Booleans. And so the semantics of the languages that we'll see, so I'm not planning on getting into like computability theory stuff, basically tells us that we need a language where we're computing with continuous values if we want to have soundness and have an interface where we can get arbitrary approximations. And so basically what happens here is we have to work with the real numbers only as approximations. And so if we know we can't do this by a topological argument. So since the plane is connected, there's no non-trivial continuous maps from the plane to the Booleans. In particular, so if I look at the diagonal on the plane, that's what it means to be equal. The diagonal is closed, and the off-diagonal is open. And so if I have any space A, the maps from A into Sierpinski, the continuous maps from A into Sierpinski, are equivalent to the open sets of A. Right? So an open set of a space you can think of as being a semi-decidable predicate on the space. Any other questions for now? I'm happy to go more into this stuff if you want.
The sort of computational intuition for this is if your interface to a real number is getting more and more accurate approximations, you'll never be able to say for sure that two numbers are equal.
Right.
Or, right?
Yep, exactly. And if they're different, then eventually you'll get approximations that will be able to tell them apart.
This is interesting because although you could, if you wanted to like implement equivalences in like square root of 2 squared is 2.
So Marshall actually kind of does do this a little bit. It's a little bit smart. So to make things more efficient, it tries to do some computation to falsify things. So this will be incomplete. So this is a little bit like you want to imagine semantically that this is non-termination, but here it discovered, hey, I'm not so stupid. If you give me 2 less than 2, I know that's false and I can stop working.
So values of the Serpensky type can be printed as false?
They can, but
yeah.
I would say for the purpose of this talk, you might want to imagine that this is not possible. Imagine it as not as just non-termination. It's simpler to think about the computability properties.
And you can get a stream that ends in true.
Yeah, I've got that example right here. right? So here's something that's true, but it's not obviously true, right? You have to do a lot of work. Like, I wouldn't know that it's true, of course. So we have to do a lot of work to approximate square root 2. And so we get a couple of question marks before it discovers, hey, this thing is actually true. Yeah?
In the first example, with the very large numbers, why does it expand and contract the way it does?
So I think it's kind of, it's a little bit misleading how it's expanding and contracting. It's just the length of the decimals, but you see the intervals are actually getting finer and finer. So the exponents are getting smaller.
Ah, I see. Okay.
So it's running with more and more precision each time. So it'll have more decimals. But then here we're just getting the smaller numbers.
Shrinks by power of 2. It's kind of funky.
Yeah, so it's using arbitrary precision floating point.
I see.
So at certain levels, it's like that's the most precision you'll have once you go, add this catastrophic error.
Right. Okay.
Okay, so this is actually a good lead into talking about the Bellin-App quasi-booleans. So this is sort of annoying because, if I want to know, oftentimes we want to pair together two semi-deciders, essentially. So if I want to compare real numbers, I can't compare them, right, because there are no continuous maps like this. But what I can do is I have an open set for one being bigger, and then I have an open set for the other being bigger. And these are sort of naturally matched with each other, and so it's useful when we're programming to just pair together open sets like this. So, but if I have two continuous maps from A to Sierpinski, right, that's the same thing as one continuous map into Sierpinski squared, right, the product. So this thing is useful to study on its own, and we use the script B for this. So basically what we think of it is we think of these as pairs of proofs and refutations. So is true is basically what it means to be true, and what is false is what it means to be false. And so here is this comparison, where we have an open set for recognizing one is bigger than the other, an open set for the other, and then we can think of it as non-termination if they happen to be equal. So we can start doing these, and unfortunately I have fancy printing that a little bit obscures the meaning. So basically it recognized that this was true, comma, false here. So if I have pairs of values, we get pairs of approximations as we go in. And so if I actually do true, comma, false, it prints that. And then false, comma, true is the other one. So 1 less than 0, that is false. I can refute it. I'm able to refute it with computational evidence. Just as with 0, 1, I can prove it with computational evidence. But if I have 0 less than 0, this is if I have 2 less than square root 2 squared, gotta make this thing work a little bit. We get these question marks, which you can think of, they're really pairs of question marks. I'm just printing it slightly differently here.
So the XOR always has to be true.
What always has to be true?
The XOR of the two values.
The XOR always has to be true. No, so in this case here with 0 less than 0, this is false, comma, false.
And can you run what this means again?
Basically, I wasn't able to prove or refute it. It's a sort of formal object where we're just pairing two logical things together, these two semi-deciders together.
What are you, false, comma, false, or true, comma, true? Or is there an example where you get true, comma, true?
So you can think of that if I have two open sets that are overlapping, right? So instead, the issue with this comparison is that it's partial. It won't terminate if you give two things that are the same. You can instead do an approximate comparison where if they're really close to each other, you can say either way. You can say true or false. And that would give you one where you have a true, comma, true if you're in the middle.
So it is kind of like I reached the point of computation that you asked me to do, and I can't decide. So it's kind of like true, comma, true.
So true, comma, true, literally, we can do it. So let's do an approximate comparison. Let LTA, so we'll give an epsilon, and then we'll compare two numbers. And we'll say, okay, what does it mean for A to be,
Do you need to make rule?
now they're
Okay.
just pairs.
Okay.
It was simpler. So let's see, A less than B, right, so the normal thing is A less than B less than A. But we can make these overlap by saying,
Plus minus epsilon.
is that the right way? A is less than B plus epsilon? I think that's the right way.
Yeah.
We can check. So then we have LTA and let LT prime, let's just pick epsilon as 1 for a second. So if any of the syntax is confusing, please just ask. And I'm happy to explain syntax. Okay, so now we have our approximate comparison. And so now I do 0, and so I've made it, sorry, I changed basically how it prints things. So it will,
It's true.
this is true, but it may discover that one thing is true before another.
There's a convention that
Oh,
you're going to have non-overlapping sets, and so as soon as it discovers one that's true, it assumes the other one is
exactly. Yeah, so surprisingly, for this LT prime 0, 0, it discovered the true part before the false part, so it just said, I'll cut off and I'll return to you.
And yeah, that was the EXO question.
That is a convention just because of how I programmed the display. I could turn off the part that says stop and just have it display a stream always, and that would be the better way to think about it. Any other questions? These are all great questions. Okay, so when we have these Booleans, we can do all the Boolean operations. So true, right, is true, and then it's not false. So when I write true on this side, it becomes top, and when I write false on this side, it becomes bottom, just to compare the two sides. Also, real is this, and then bool is that. Okay. So in particular, the interesting thing is now we have a notion of negation. So if you go back to the Serpents, just for the topology thing, you can ask, can I have a continuous map that exchanges these two? Well, if I had a continuous map that exchanges these two, the preimage of this has to be open, but it's not open here. So I can't do negation. But we can do a sort of negation on these Bell-Map quasi-Booleans. We just exchange what it means to be true and false. And so similarly, we can do things like and. Well, what does it mean for x and y to be true? Well, we need x to be true and y to be true. And what does it mean for x and y to be false? We need x to be false or y to be false. So here we see that we have two maps on their Sierpinski space. We have and or, which are continuous maps from the product of Sierpinski with itself to Sierpinski.
Are they not just Sierpinski square? Or... Oh, I see. The ones that you're
The
using
and and the
inside.
or
Yeah.
on Sierpinski. So Sierpinski has and or, but it doesn't have negation.
Oh, this is conjunction.
Yeah. So we can use this, and now we can describe compact sets, essentially. These is it's a space, a topological space. Essentially, it's a generalized space for compact sets. And what it is we're just going to be in our programming minds right now. We'll think of this as a for-all quantifier. So think of E as being like R2 or R3. We're going to describe shapes in R2 or R3. And so what we're going to do is if you give me a predicate that returns as B here, the Bell-Map quasi-Booleans, I will tell you whether it's true or not, whether it holds for every point in my compact set. So let's start with some simple examples. We can implement the empty set. What does it mean for P to hold everywhere in the empty set? Well, no matter what P is, it holds. So I just return true. And I can construct a shape that has just a single point in it, because if I want to know if P holds everywhere in that single point, I just return P applied to that single point. So there's the unit interval here, which is basically a primitive, so I won't go into that. But this is like very important. So we'll look at how this computes a little later in the talk. So importantly, we have point, which is the return of a monad. And then we have compact union, which will be the bind operation of a monad. At least when we're thinking functional programming, we tend to use these sorts of notions for strong monads.
I have questions about
Yep.
syntax.
Yep. Okay.
So it's how do you call a function, and how do you specify the arguments?
How do you specify? Just spaces application.
Uh-huh.
So if you're familiar with like OCaml, for instance, it basically works like that. So you don't see it here. Sometimes you have explicit type application, which is annoying.
And the colon is like of type.
Yeah, so what this says,
Uh-huh.
so the E and the F are type variables. They can be any type whatsoever. So think of it, it could be any space whatsoever. And then this is if I have a K shape over E. So if I have a shape in E called I, and if I have F, which is a function that takes points in E to shapes in F, then I get a shape in F.
And what is the difference between the single and double arrows?
So single arrows are for function types, and then here this is a lambda that says if you give me a P, here's what I'll do with the P.
Oh, it's like a definition of the lambda.
Yeah, so when I have a lambda, right, I abstract an argument with a name,
Yeah.
and then here's the type of the variable that I'm abstracting, and then here's the result.
Is that a different arrow symbol?
Yeah, is it really?
Yeah, there are two arrows.
They're very small, aren't they? Yeah.
But it's a double. Is it
It's a
like
double
that?
arrow,
It's a
yeah.
double arrow.
So compact union, right, basically allows me to construct a shape by, I had a good example with a cone, but it allows me to construct, for instance, if I want to build a cone, the surface of a cone, I can build a line segment, and then for each point on the line segment, builds circles. And then I can take the union over all of those circles. And so there's infinitely many circles to take a union over, but it's indexed by a compact set. So we can do that to produce a compact set.
So I is an index set over which you're taking a compact union.
Yes.
Or E is, right? Or
I
is the
is the
oh,
I is the index set. So think
Oh,
of
I
it,
see.
E here would be the real line because I construct a unit
okay,
interval
and you have a
within the
subset of
real
that.
line,
I see.
but I'm taking a compact subset of the real line. Okay, so we can do lots of constructions. I don't think we necessarily need to go into this stuff, but we can construct a square. Well, how do we do that? It's just do a compact union of an interval and build another interval off of it. And then I can construct a disk, for instance, by taking the square and then saying, all right, well, either for this predicate, either it holds everywhere. If I'm a point in the square, either I require P to hold, or you can be outside of the circle. And that lets me implement the unit disk. So this is all this ways you can program with these K-shapes. And all of these K-shapes are higher order functions. So it's not yet clear what do we mean if this is a language for continuous maps, what these higher order functions mean even. But once we've constructed K-shapes, we can do various things with them. So the key things that I'll point out, that's unfortunate printing. That's inf. For Infimum. I had to do the prime because otherwise...
I have a question.
Yep.
So, like, is this programming like I'm defining a space and then I'm kind of like masking the space with like true and false values on every point, and then I'm getting a new space? If I
So
just
I'm
get one of the
defining
truths.
shapes. So I'm trying to distinguish between shapes and spaces.
Yeah, yeah,
So
so
like
that-
space being this where a shape lives.
Right.
So the shape is a quantifier. So we'll see now like kind of what that means, how we can compute with it.
The thing that you're talking about is the O-rep, right?
Yes.
You're thinking of a common way of representing shapes, which is to have a predicate that takes in a point in a space and says, are you in it or not?
Yeah,
This is different because in order to specify a shape, you need to provide a function that takes in an arbitrary predicate and tells you whether that predicate holds for every point in the shape. So it's a...
And what is the predicate in this case?
It could be anything. So
But
if I'm
it
a
has
shape,
to be-
you have to be able to ask me, is every point within U less than 2? And I have to be able to say yes or no. And then you ask me, is every point within U you know,
Oh,
you-
so
you-
Except its preimages have to be open, right? So you can't just have like a delta function.
they're
at a
continuous
point.
functions. yeah.
Preimages have to be, sorry, the preimages of,
The preimages of like true and false. Like a predicate can't literally be any function to.
yes, you're
Yeah,
you're not required to take any predicate, right?
Right.
You're taking it and it's sort of your,
Yeah, it has to be continuous to B. Right?
yes.
So, okay, I need to understand this. So, the shape is carrying a function.
The shape is
The
a
shape
function.
is defined as a function,
Okay.
that's like all it is. It's,
Okay,
all it is this quantifier.
And then I ask the shape, is this
The function's argument is another function.
okay.
So in order to interact with the shape, you have to construct a predicate function.
Yep.
And then you ask the shape, is this predicate function true for every point in U?
You're basically allowed to ask it for any open set, is it inside the open set? I think. And so you can consider it as like an intersection of a bunch of open sets. Is that
You
fair?
can, for any open set, so another way that you can think about it is that I'll tell you which open sets in a semi-decidable way, I can tell you if I touch an open set, and if I can tell you if I'm contained entirely within an open set.
Oh, I see.
So,
Yeah.
but both of those will be in semi-decidable ways. If it's true, I can tell you.
Mhm.
If it's false, I might not terminate.
Okay.
And that is not at all obviously equivalent to what I'm giving here.
So I'm also wondering, sort of like, how should we think about the topology of? But can you go back to the compact union?
Yeah,
How should we think about
maybe.
the topology of the space which little f lives in? So it's like, because so it's presumably some sort of continuous map from E to the space of shapes, right? And we want it to be continuous in some sense because it can't be arbitrary, because otherwise you could construct very non-compact pathological things by
Yep.
unioning each other. So like, what should do we take the compact open topology, or?
That's a great question, which I'm planning to address in the latter half of the talk.
Okay.
So
Okay,
let's
good.
hold on to that question for now. Although it would probably be good to actually just switch that right now. So let's look quickly at an example of using a k-shape to compute a number. So we have this primitive called Dedekind cut, which is another higher order function, so we need to kind of explain how that works. But so Dedekind cut has a type that looks like this. If you give me a predicate on the real line, and it only works for special predicates, I'll give you a real number. And the idea is, if I want to describe a number, what I should do is describe what it means to be less than that number. So we can look at the square root of x, right? So what we need to do is say, what does it mean to be less than the number? And since we're using these paired predicates, we're really giving an open set for what it means to be less and an open set for what it means to be more. So I should have the definition of square root somewhere here. So square root is using a Dedekind cut. What does it mean to be less than the square root of x? Well, q is less than the square root of x if q is less than 0, or if q squared is less than x. And this gives us the way to compute square root. So this is how we've been looking at. This is the definition that we've been using, for instance, for this. Okay, so we can also use this with our k-shapes to do, look at the infimum here. So I wrote for all here, but a k-shape is its for all quantifier, so this is basically nothing. So we say, what does it mean to be less than the infimum of, so here I have a k-shape on the real line. So a shape on the real line, what does it mean to be smaller than the infimum of it? Well, it means that for every point on that line, I should be smaller than that point. So this gives us a computational way of describing infimum.
Can you explain what how k represents for all?
We sort of do it by construction, right? So we started with empty, and you would say, right, this is the for all quantifier for the empty shape, right? And then point, you say, you look at this and you agree, yes, this is the for all quantifier for a point, right? And so then if I have things that combine them, like compact union,
You have a composition.
you know, if this thing is the for all quantifier for a shape, and this thing produces for any point in E for all quantifiers, the result will be a valid for all quantifier for the indexed union.
And this is handled by the machinery behind the language.
Um,
Or
In what sense, I guess? So
Like-
the functional programs there are implementing the computational behavior.
No, it's like the conjunction of like for all and for all, like that happens somewhere like behind the scenes. Or
It's
like
the definition of a shape. It's what we were just talking about a shape being this function.
Uh-huh.
That's all you need. So
Oh,
when k is the function, we're just applying k,
Yeah, yeah,
and
yeah.
that asks, are you true for
But there
everything?
seems to be a fundamental for all which doesn't reduce, which is for your unit interval.
Unit interval is a primitive, yes, and
But
that's
how do
where a
you-
lot
so how
of
do
the
you
magical
do that?
computational behavior comes
Okay.
in,
Oh.
and where you have to start thinking, all right, unit interval is a higher order function, but it's a primitive, so I have to implement it as a primitive. What does it mean to implement a higher order
And that's where
function?
you use this interval arithmetic. At the, is
That-
that what happens like in the
We'll
machine?
see it in a
one
little
day?
bit. All right, so here I think, so do you buy that now we can compute infima? And we can do some interesting things with this because we can do suprema as well. We just use exist instead of a for all. And we can use this to implement the Hausdorff distance. I'm just going to spell this out so it doesn't look ridiculous. If you're familiar with the definition of a Hausdorff distance, it's just defined in terms of some suprema and some infima over a distance metric. And so we can write this as a functional program. It's basically the spec of it. So I have a slightly more compiled version that you should think of being as equivalent if I had written some compiler optimizations. But so I can take my constructed square and the unit disk that lives inside the square, and I can ask what's their Hausdorff distance, and I can compute that right here. So we'll compute this, and we will get a very slow convergence to a particular number. And this is a fun. Anyone want to guess what the number is, or tell me what the number is? Looking there. So this is just
Square root of
It
2
says-
minus
this is radius
1.
1, just to.
Square root of 2 minus 1.
Square root of 2 minus 1. Oh yeah, because I have the answer also
Oh, you
on
did.
the other side.
I see.
Not that. So we have an approximation there, and here's a much quicker way of computing the same number. But what you can see is this will satisfy the thing. If you wait long enough, it will produce an answer that will converge to square root of 2 minus 1. Okay, so randomness, we have measures, and instead of being for all quantifiers, we're just going to implement a measure as its integral. So similarly, we have a monad.
Over the whole space of this function. The
Right.
integral, yeah. Right.
So
mu of
if I
x.
have
Yeah.
a probability distribution, let's say on the reals, right, it says if you give me a function from the reals to the reals, right, because integrals are always real valued, I'll give you the integral of it over my distribution. So Dirac delta is the return of the measure. And then bind, these are really actually the same functions as we have for the shapes. Both of these have this continuation passing form. And so we can play the similar games. I can construct a Bernoulli measure, right? So what's the integral of a function f? Well, it's going to be p times f of true and 1 minus p times f of false. So we have a primitive that gives us Riemannian integration. And so that gives us uniform distributions on the unit interval here. So we can do similar things, and we can even do some probabilistic programming stuff for the probabilistic programming people in the room. So I can construct a measure that says, okay, sample from a Bernoulli, and then depending on the results of the Bernoulli, oh, that's not the one I meant. Beta Bernoulli. We can do a beta Bernoulli. So I have a beta distribution, and then I observe that I sampled a true. So then I draw a Bernoulli, and I observe that the Bernoulli is true. And so this is sort of a convention where we construct a measure where we sort of weight the measure according to the likelihood of the evidence. So what this is doing is, this is a measure that on unit, it has no information other than size. So this is equivalent to a real number. But what it's saying is, I'm going to put more weight on true and less weight on false here because I observed a true. So I get this measure, and then we know the whole thing that we do in probabilistic programming. To get the posterior, we just normalize the measure. And then so I can ask for the expectation of that, which is the integral of a particular function, x. So I can...
So you, instead of writing expectation, you could have just applied that measure to the identity.
Yes, let's do it. And we get this will converge onto 2/3. Okay. Well, these are all great questions and stuff. I have around 5 minutes to get to the semantics of higher order functions. So let's skip to the interesting stuff. All this stuff.
You have like
through
10 or 15 minutes left.
Okay. Okay, so the basic idea is, right, so we can think of it sort of denotationally in terms of, so we're just going to imagine we have a language for first order things right now. So this won't explain the higher order stuff. We can think of it denotationally in terms of topological spaces, right? We've been doing a lot of reasoning with continuous maps. And the key thing is this is not closed, so we can't really think about function spaces in the general sense. And then we can also think about these stream approximations, which is how it's implemented. So this is a little bit more of a computational view, where you can think of it as if, for instance, for the real numbers, we had these pairs of floating point kind of things, multi-precision floating point things. And a function like sine, for instance, was taking approximations of the floating point and producing approximations, but that function could change also over time. So this natural number is just indexing time. So realize if I have a point, the A here will be just the terminal object, right? So this will just be a stream, nat arrow B of values, right? And that's what we saw whenever we had real numbers.
So the countable set in this case has a particular order, right? Or we have a particular mapping from n to the set, the objects of
you're saying that it's
given
decreasing, it's descending. Like it's getting more and more precise. Is that what you're trying to say? It has an order?
Or I'm just saying, does a stream come with like a canonical mapping from n to a stream on a, or am I?
No.
The objects of this.
So points are streams.
Yep.
Looking at it, so the basic idea is so this R, right? We had these pairs that we saw there of a lower bound and an upper bound, and so the countable sets here are things like that. Those pairs of lower bounds and upper bounds. Did that answer your question?
Right, these are the types.
Also, so you're just implementing stream here. That's kind of
yeah.
Okay.
So that's, but I'm trying to actually map this to a particular notion of spaces, and so I'm not gonna let the sets here be uncountable. I'm gonna force them to be countable. Partially, you can think of it because I want to print the things on the screen, right? And so if I want to print something with finite information, it better be a countable set. If I allowed uncountable sets, you'd say, well, what's the point of thinking in terms of topological spaces in the first place? Perhaps. Okay. So points are these streams of approximations, and then first order functions. Now, if we think at least in terms of the streams, right, they're taking approximations and they're producing approximations, and in lockstep in a certain sense, right? So given this approximation, we're looking at the squaring function, right? We saw that square root 2 squared, and it's pretty easy actually for positive numbers, right? We can just square the two endpoints, and that'll give us a good approximation to this. And so that's what you see is happening here. So that's an example of how we compute with some of these first order functions. So here's some simple arithmetic functions that we have. And so the interesting thing you'll notice is that you're allowed to depend on n, right? So this is that natural number for the stream, but most of these arithmetic functions aren't doing it. The key one that does is Dedekind cut. So it might seem here like the n's are sort of superfluous, that all we're doing is mapping approximations to approximations, but Dedekind cuts are getting tighter. Right, so if I want to negate an interval, right, all I do is I negate both of the things, but I swap the endpoints, because now what I thought was the highest is now what I think is the lowest. And adding two approximations works similarly.
Wait, sorry. What are the x's that are in the interval?
the x's that are in the interval.
So the
So
x-
the
the
square
x
brackets
over-
are just notation. You can think of these as a pair of numbers.
Yeah, but what type is the number?
This is I'm thinking of them as rational numbers. It can be multi-precision floating point, but also it can potentially be negative infinity or positive infinity, but those are just for convenience. We don't need to think about it.
Right, because at the end of the day, you are still implementing in floating point, but kind of
Multi-precision floating point. So all you need really is a dense, a dense countable subset of the reals. Right, that'll give you enough to get arbitrary approximations. So those are the primitives on the reals, and then we have primitives on the Sierpinski space as well. So these are the primitive functions that we were doing, and it's this kind of things you can expect of semi-deciders. So if I have two semi-deciders and I take the AND of them, basically to return true I need to observe that both are true. But if I haven't observed that yet, then I have to just say I don't know yet. Okay, so that's the first order stuff. Let's get to the higher order stuff. Okay, so basically what we're going to do is neither of those categories that we just saw were Cartesian closed, so we'll just take presheaves over that category. But the important thing that we want to know is if we ever have a first order object, it should be the one that I expected from the original category, right? So we've been programming in this thing that has higher order functions. But when I return, first of all, a real number, I expect that real number to really look like a continuous map, right, from the 1-point space into the actual real numbers, right? And if I had a function from R to R in my language that was higher order, I want this to actually correspond to a continuous map from R to R. So presheaves are great for this because they'll take any category and they'll add in products and exponentials, and they'll preserve products and exponentials when they exist. So I don't know if I should explain like Uneta with products and exponentials. Would people want to see that? I don't know if this is like probably hard to balance like already know it versus don't have the background for this to make any sense in a few minutes.
Let's continue. We can talk about it in question time or
Okay.
coffee.
So that sounds good. Here's the key thing, second order functions. So all of these examples of primitives that we had, Suprema, Infima, Dedekind Cuts, all of these were second order functions. And what I mean by that is they sort of had this flavor. So I'm using this overline notation to mean the Uneta embedding. So what that is I'm taking my space, something that really came from the lower category, and I'm lifting that into the category of presheaves. And so we are going to have to implement a bunch of primitives that have this shape. So the reason that I have the 1 here is because they're constants. They're allowed to be used in any context. And so as a constant, it's basically just a point of this thing. But we know this is really equivalent. We can just use the law of exponentials to say it's equivalent to this map from an exponential space to the C. And then here I'm using this N notation, which I really just learned about recently. But the way to think about this is that for any space gamma, so gamma comes from the original category, this category that may not be Cartesian closed, right? We need to produce it. It's a natural transformation from this functor to this one. So it's from this presheaf to this presheaf. And so we can just expand out the definitions of these two things. Or actually, this one requires more work. But I guess you can take, well, this is sort of an unimportant fact here. So if I have this, it is equivalent to this. And why don't we actually go through that fact? Because here it is. That fact is right here. So we have to use the definition of what it means to do the function space for presheaves. And that's this definition here. And so here I'm just expanding out. This is by definition. Here I'm just expanding out what it means to the Uneta embedding means. And then here what I say is I have delta into gamma and delta into A. Well, I can just combine them. It's a delta into gamma times A. And now I have, for any delta, a natural transformation from this into this. And so this is the Yoneda lemma, right, that says, well, you know, this is pretty much the most general thing, so you can imagine sending delta to gamma times A, and this becomes the identity, and I just get gamma times A into B. So when I have a function, this is really like the key thing of thinking about second order functions. If I have this thing, it really looks like a map, continuous map from A to B, but I take some extra context gamma along.
So what is gamma?
Gamma is any context. So you can think about it as, so here, think about it as a space. Or if you're thinking more computationally in terms of those stream approximations, it would be something representing a stream approximation.
Mm-hmm.
So it may be, you know,
So
pairs of real numbers that are, like oftentimes when we're programming, we live in, like, we have open terms essentially. We might have variables that were bound earlier and we want to work abstractly with those variables, and that's often what gamma represents. So we talk about it as like a context. But that's my view on this. Of course, the math doesn't necessarily say you have to think about it like that.
And these A to B are like any first order functions?
So
Or
A and B here are spaces. So they have the same type as gamma, right? Gamma, A, and B are all spaces, and that's how they all sort of live here in the same syntactic category. But A with the overline is the Yoneda embedding of A into the category of presheaves. Okay, so really a second order function in any category here is going to look something like this. What it's going to do is for any gamma, you have to take, let's say, a continuous map. I'll just think about it like this. From gamma and A to B, and you have to produce one from gamma to C. And in particular, we've often been looking at when B and C were the same thing. For instance, both real numbers or both Booleans. And so it kind of looks like I have gamma and A into B to gamma to B. And so it's like I'm removing one thing from the context. And that's how these things seem like quantifiers or continuations or things like that. Right? They're going to range over the possible values of A in a particular way, but they'll do it nicely behaving with gamma abstractly. So for streams in particular, we get basically something that looks like this. But for all our examples of primitives, it ends up being a little boring. It's kind of what you would have expected anyway. We're going to implement the primitives as being streams basically that take functions from A to B, where those you can think of that as being a whole collection of approximations of B, depending on an approximation of A that you give, and I'll give an approximation of C.
2 minutes.
Okay. So let's look at the primitives. Here's one, integrate, which we'll say is integration from over the unit interval from 0 to 1. And so what this is going to do, here we have finally a dependence on n. So it's producing real numbers. So since it's producing real numbers, it's going to be these streams of approximations. And we know that f takes approximations as inputs and produces approximations, so intervals, let's say. Right? So the intervals that I'm going to feed it are just intervals that break up the space into a bunch of partitions. Right? So if I have 0, 1, at first, maybe I'll break it into these two things. And then the next time, I'm going to subdivide again. Right? So I give f, and I say, apply it to like 0, 1/2. And then this will give me another interval approximation of f's behavior. It might not be good, but as I feed it finer intervals, I'll get tighter outputs. And so this will give me a stream of approximations to the integral. And we know that as I subdivide further, the approximations will get better. And so similarly, we can do the quantifiers. Basically, we're doing a similar sort of search. Well, I'll partition up the interval. If I want to know that an exists predicate is true on the interval, it suffices if I find it true at a point, then I'm good. So I'll just try f at a dense set of points. So this is what it's saying is, I'll try some finite set of points, and each time, as I go through the interval, so first I might just try these three, then the next time I might try at a denser thing, and then I'll get even denser. And eventually I'll enumerate a dense subset. Right, and we know if I have an open predicate that's true somewhere on the unit interval, it's got to be true at some point in my dense subset of the unit interval.
And for all, do you cut the computation for the largest n? Or
For all, so for all, I can't test at points, I have to test at intervals. And so basically, the guarantee that I have is if an open predicate is true somewhere, it's going to be true for an entire compact set somewhere. Sorry, I have to check that it's the for all. So I'll break it up into compact sets. And if basically I know that it can't be so fine that if I subdivide enough, eventually all these approximations will give true. Okay. I'm happy to end here.
Okay, thank you.
Yeah, if you guys have any questions, I guess we'll go chat, coffee.
Yeah, unless anyone has a burning question right now. No? Okay, thanks again.
Thank you guys.